Right. So let's have a look at some examples of linear programming applications. We'll look into these sort of more general type of models, but they are actually structures that are going to appear all the time in examples we're going to see in our course. We'll start with resource allocation and then looking into two different type of models, one being transportation models and then production planning. So let's get started. So basically the logic behind a resource allocation is it's that you have a collection of resources to which you're trying to distribute in a sort of a production setting in a way that the final production assortment you will obtain maximizes a given uh, profit or perhaps minimize the cost. And this plan of maximum profit or maximum revenue or minimum cost is would be then an optimal plan, right? So how do we do that? In order to state this problem setting in a mathematical programming language, so it can be a model that we can then optimize, we need to define some entities that will compose the building blocks of our model. So we'll start with so basically what we have is defining what are the entities in our problem, which in this case are the resources we use and the products we are going to make. So the resources are defined by a set I of elements little I, and I have capital M of those. And the set of products are represented by J, and I have capital N products I can make, each of them represented by little j. So in this case, each product I make gives me a return per unit of Cj, and I can't make infinite amount of products and have an infinite return because my products, they require resources to be made, and I require exactly a of the resource I to make product J. The reason why I cannot make infinite amount of products is because each of my resources they're limited. So I have an availability of resources that I have to observe. And my actual plan then is defined by these variables xj, which represent the amount of product j I make. So with these elements, I have everything I need to be able to state my problem, because basically what I'm trying to do is decide. So I have to make decisions in terms of how many products xj I make for all j. So that's my decision variable, right? My objective is to figure out, it's the way I measure, figure out how how plans are different, how they differ between themselves, is simply by comparing how much revenue they make me, how much return I get from that, and that is calculated by seeing how much I make of each x product j, multiplied by the per unit return, and then I accumulate this number among all my products. And that expression here is giving a plan x, which means amounts of product x1, x2, x all the way to x capital N I make. This is how much income I get from it. And that my objective is to find this plan that maximizes this expression. But the reason why I can't make infinite amounts of x1 and infinite amounts of x2 and so on is because I have a constraint. Put it here, constraint that says serves the amount of resources I have available. So the amount of resource I use is basically given by, if I consider that, considering the amount of j I make, product j I make, and the amount of resource I use in making product xj, and then I look across all the products I make xj, J in J, in capital J even, this has to be less or equal than the availability of resource I. And this here is basically telling us the amount of resource I used in the plan X. Being X, this vector composed by X1, X2, all the way to X capital N. And that has to hold for every resource I am considering. And that's all I need to write my optimization model. That's how I state resource allocation into a math program, a resource allocation problem into a math programming setting. So you can see here that with these elements, there is another constraint missing here. The fact that I'm gonna put it here that I cannot make negative amounts of products, right? Very important. With all these elements here, I'm able to express my resource allocation problem as a mathematical program, which was our original intent. Okay, so let's go over a little bit more detail of these main elements here. So the first one is the objective function. So like I was saying, it measures the quality of a plan. So suppose we have a vector C that, you know, has for product 1 and product 2, it is like 2 and 4. So that's the amount of money I make with product 1 and with product 2. And suppose I'm comparing two plans. So I have a plan 1 where I make 2 units of X1 and 1 unit of X2, and another plan where I make 3 units of X1 and 3 units and 1 unit and 2 units of X2, say. So in this case, what I get is that my value, the value of plan 1 is 2 times 2 plus 4 times 1, which is 8. And the plan, the value of plan 2 is 2 times 3 plus 2 times 4, which is 14, I think. Yeah. So clearly, Z2 is a better plan. Plan 2 is a better plan than plan 1. Oh, sorry, I didn't realize I was in front of it. Let me move this a little bit, like so. There we go. All right. So that's what my objective function is doing. And of course, this thing here is representing a dot product, which is a more compact way of writing that expression. The other aspect associated with it is the constraint. So basically, the main constraint we have is this constraint that we just expressed. So it's basically saying that, so in our two product example, if I use, say I use A1 to make product 1, and I use A12 to make product 2, and I may use A21, it's another resource, so I equals 1, I equals 2, and I have A22 for product 2. So when I look at the amount of resources that I'm using to make product 1, sorry, the amount of resources 1 I'm using in my production plan, I have to take into account the amount I use for product 1 and the amount of use for product 2, which means that I have to make sure that A11x1 plus A12x2 is less or equal than B1. So that's the requirement for product 1. And I'll have another one for like this for product 2. I can write here just for the sake of completeness. So the amount of resource 2 that I use to make product 1 plus the amount of resource 2 that I making product 2 has to be less or equal than B2. So this collection of expressions is what is represented by this. By the way, this is the means subject to. It's just we use an sort of a um God, what's the name of that? It's not an acronym. It's abbreviation, right? And the same here means maximize. Um, so yeah, so these two expressions is what's represented by. So let me do this. These two expressions here is exactly what is being represented by this thing here. See, which once again we can also put in a matrix form, just like having this as our matrix A, multiplying by a vector x, so transpose x1 x2. It's just a dot product. Well, in this case, it's a I don't need that. Sorry, I was thinking something else. There you go, matrix multiplication, right? And that equals b1 and b2, like so. Yeah. And so that would be a x equals b, just like that. So here it is. My matrix is m by n, which is kind of unfortunate that I had two products and two resources, so I get a skewer matrix, but I think you get the point. And I have a vector b that has m components, and we're also requiring that the variable is non-negative. Sometimes we're gonna write this like so, and that means that is non-negative component-wise. So each of the components of x is greater than or equal to 0. All right, so let's have a look at a numerical example of this resource allocation model. So so we're looking into this paint factory that makes exterior and interior paint and uses these raw materials M1 and M2. So it has a maximum demand for interior paint, and moreover, the amount of interior paint produced cannot exceed that of exterior paint by 1 ton per day. So basically, this is a resource allocation problem, just like the one we discussed before, but it also has on top of it additional business rules that we have to represent using constraints. So the resource requirement is on this table, and you can see here that this is exactly like that matrix A we were talking about with the amounts Aij. This is the same as that vector B we were just talking about as well, and these my profits is the coefficients for my objective function. So we can quite readily define. So let's define that we have x1. So first step defining the variables is that x1 and x2 are my exterior and interior paint amounts in my plan. Then the next step is to define the objective function. My objective function here is going to be maximize my revenue, which in this case is given by C1x1 plus C2x2, or let's use actually use the numbers, right? So that would be 5x1 plus 4x2. And then finally, my constraints are going to be, I have the resource allocation constraints. So the resource allocation constraints, for constraint relating to M1, what we have is that 6 times the amount of exterior paint I make plus 4 times the amount of interior paint I make has to be less or equal than my availability of resource M1. For resource M2 is exactly the same. I have 1x1 plus 5x2 less or equal than 6. That's the availability. The amount, this is the amount of resource I use. Amount of resource I use, given that I'm making exterior paints and interior paints. And now I have the extra, so I have the extra business rules. So the first one is related with this. So the maximum demand for interior paint is 2 and interior paint is x2. So that's telling me there is no point making more than 2 tons per day of x2 because I don't have demand for that. And that's how I express it with a linear rule. In this case, it's pretty obvious that I only have one variable. And the other rule is saying that the amount of interior paint cannot exceed that of the exterior paint by more than 1 ton per day. So when I look at the amount of exterior paint I make, which is x1, and I compare it with x2, let's put it like that, which is the amount of interior paint, what I'm saying is that the amount of interior paint cannot exceed that of exterior paint. So the amount of interior paint has to be less or equal than the amount of exterior paint plus 1 unit. Sometimes you have to be careful with these because it's quite easy to get them wrong. Let me just put this a bit better, easy to read. And I wrote it like that as a greater or equal than constraint. But to be honest, this is the same as saying that x2 is less or equal than x1 plus 1. You can have any time. And these here for my, let's call them business rules. These 2 constraints. And finally, the last thing to say is that x1 and x2 are greater or equal than 0. And now combining my objective function and my constraints, I have a mathematical model that I could use to represent the production, the optimal planning, the paint factory production planning, and figure out what is the optimal production plan. So this is what I have here. This is written in a more standard format with the variables on the left hand side instead of the right hand side, but this is the same as what we had with x2 less or equal than 1 plus x1. Right? So this is our model right there. The resource constraints, the business rules, and the requirements of being non-negative. Right? And by the way, we can also, we can still represent in this compact sort of resource allocation form like we see, because honestly, this is can be basically any linear program you can possibly think of. The main difference is that I have my matrix, my vector C just like so, but my matrix A, instead of looking like just 6, 4, 1, 2 like this, it actually gets augmented to include these with a coefficient 0 for x1 in there. So it looks exactly like that. So 6, 4, 1, 2, minus 1, 1, and 0, 1. Okay, so this is a numerical example of a resource allocation, which is basically the main sort of type for linear programs, really. In a way or another, every LP is a resource allocation problem. Right. The other type of problem that we have that it's quite interesting in the sense that it appears quite often and it has interesting practical applications is transportation problems. So basically, transportation problems involve the definition of a production plan. So basically, you have a collection of production plants, say, they are supposed to produce determined given products and then send them to clients. And what you have to take into account is basically what will be the amounts produced in each of these factories, these plants, and how much is going to be sent to each of the clients, taking into account things like production costs, perhaps, but most importantly, because it's a transportation problem, transportation costs, which are associated with the transportation arcs. And of course, my factories, they have limited capacity, which is sometimes what makes the problem more interesting. And of course, I know the demands of my clients and I have to meet them. So in order to represent that, we're going to follow a similar strategy, and we'll start by defining what would be the entities and so on. So for here, this is a small example. So I have some cities in the US, and I want to send products, I think, from San Diego and Seattle to New York, Chicago, and Miami. And here are basically the information I need to define an optimal distribution plan that could look, for example, like this, with San Diego sending to Chicago and Miami, and then Seattle sending it to New York, for example. So basically that tells me my factories, my clients, what are my factory capacities, what are my demands in each client, and this represents my unit cost from origin to a given client destination. With that in hand, then what I have to do is to write my optimization model, and we're gonna follow exactly the same logic. So let us start by defining our entities. Our entities here are gonna be my set of production factories that I'm calling I, and in this case it has Seattle and San Diego. It might be more convenient to, instead of having to write these all the time, name like 1 and 2. And then we'll have our clients 1, 2, and 3. Okay. So that's my entities in my problem. The next thing I want to decide, so it's define what needs to be decided, and how I'm going to access a given solution. So in this case, my decisions are basically related, let's call it X, which is the amount of product I send from plant A to client J, right? So XJ is the amount from location from plant I to client J. And what I have, well, if I have 2 plants, 3 clients, what I have is 6 of those to decide. And how I'm going to classify, or how I'm going to evaluate a production plan? Well, it's going to depend on the amount it costs me to do the distribution plan, and that cost is going to be given by the unitary cost of sending a product from plant I to client J times the amount I send from plant I to client J, and these all summed in for all client J's and for all production plants I. By the way, quite often what we're gonna do instead is just write this like this: I and J of Cij Xij. This is just a shorthand for this double summation. Okay. And that's how we assess our objective function. Because we're not, crazy or anything, what we want to do is to minimize our costs, which is exactly what we have here. But here what I have is it's with the actual numbers, right? So more compactly I wrote like so, but if I actually look at the costs, I get these elements. All right. And finally, what are my constraints? Well, what I have in terms of requirements is that whatever I send from a plant, so suppose I have a plant I here, and this is being sent to different clients J, so J1, J2, and J3. It has to be such that when I look at all these amounts being sent, so this is X I J1, this is X I say J3. When I add X I J1 plus X I J, let's call it N, this has to be less or equal than the capacity of my plant I, which in this case could be, say, AI, which is the same as saying then that sum in all clients J of Xij has to be less or equal than the capacity at plant I. And likewise, when I look at a client J and I think of everything that is being sent to my client from all the to my client J from all my plants I, so I have I1 here, I2 here, and I3 here, for example. What I'm looking at is saying whatever gets sent from plant I1 to client J plus 2, from plant I2 to client J towards plant I3 to client J, that has now this time to be greater or equal than the demand at J, at client J, right? And that's equivalent of saying the summation in I of xij greater and equal than the demand of j. This actually could have been written simply the summation in I of xij equals the demand of j. Because you're not going to send more than you actually need. Let me move this so you can see. There you go. Because you're not going to send more than you actually need. But on the other hand, by writing it like this, you give the model a bit more flexibility in terms, because it might make sense in some specific context to send more than the demand. Say if you have uncertainty in the demand, for example, like we're going to look later on as well. But these two in this context would be equivalent, because when you find an optimal solution, you're not going to find a solution where you send more than the demand. Because you just have to satisfy this minimally, and the more you send, the more you pay for. This is going to become a bit more clear later on, but I just thought it would be important to bring it up. So that is exactly what we have here, but then with numbers, if you prefer numbers. So remember that we have 2 plants and 3 clients. So these are saying that I have to satisfy the capacity of my production plants, and I have to be I have to be satisfy more than send at least the demand of each of the nodes. With that in mind, I can then go on and write my optimization model in these compact forms. Oh, so it's C. Well, it makes more sense because it's capacity. So I think I wrote A, but it's the same thing. So basically, I can write those constraints. So these 2 constraints, let me put some colors. These 2 constraints are these, and these 3 constraints are those there. So you notice that this is a more compact form, and it's problem independent, because it means that I'm implicitly representing the replications here. So so that's kind of how it's kind of expressed in modeling languages like jump, like we've been using in our course as well, because it's detached from the input data you have. And so this is our complete model with our objective function right there, our capacity constraints, and our demand constraints, like so. And of course, all flows have to be positive. You can't have negative flows. And another way to represent that is to use that algebraic form that we were discussing. So by the way, this is kind of like the language we're going to use whenever we talk about optimization models in our course. So today is the very first time we're looking into these, so we're going very slow to get everyone more or less on the same level. But from now on, we'll mostly talk about optimization models in this setting, because that's the language we use to express them to our computational tools. So it's important that it's this language of what's replicating and what is summing. It's clear for you when you go over these, right? So yeah, and then it means that it doesn't matter if I have 2 plants and 3 demand nodes, or if I have 200 plants and 300 demand nodes, I still have the same model. It's completely detached of the data. Right. So the last problem I wanted to look at is what is called the production planning, or more commonly known as lot sizing problems. So basically the problem is the following. You're trying to plan how much of a product you're going to produce, And the difference here is that we're going to look into a setting where we're looking into a multi-period horizon, in the sense that we're not planning only what we're going to produce today, but we're also planning what we're going to produce tomorrow and the day after, or perhaps next week and the week after. Um, and the reason why we want to think ahead with our production plan is because we have available both a forecast of our demand and also a forecast of our production costs at different times. So this is a common setting when, for example, when you use raw material that is has a fluctuating price, meaning that you somehow can predict that the current price of your raw material is lower than it's going to be in the future. So what you could do is buy more today and produce now to satisfy a demand that is in the future. And the way that you can shift a production in time is by means of inventory. So you produce today, you put in stock, and then you sell later on. So having a forecast of how much is your demand and how much is the cost of your raw material allows you to play with these spreads, with these differences in a way to make a profit for you. And that's kind of how many business operates, really, and that's behind, many of many business that are based on manufacturing, and how they play the fluctuation in price of raw materials. So that's the setting we want to look. And of course, in order to keep a stock, we have to pay for it. So we have to take into account this trade-off and how much is to produce today and hold then to sell later, or then just sell later on. Okay. So basically the process goes like this. So we represent our period that we're planning. We call it a planning horizon, which is divided by in uniform time intervals. In this case, they could be months, or could be days, or could be weeks. And basically, what it represents is this sort of balance logic where we can see the amount of product we currently have as being like in a reservoir of product, or like a pool of product. And it's composed by, for in period one, is composed by, say, the amount I produce in period one, discounted or leaving my reservoir the amount I use to satisfy the demand at period one. Whatever that I produce and do not use to satisfy the demand gets sent to the next period as a inventory, as a stock, represented by S. So when I start period two, in order to satisfy the demand of period two, I can use the amount I had in inventory transferred from the last period plus the amount I actually produce in period two. And of course, some of them might even be zero. So I might be able to satisfy the demand of period two just with what I have in inventory. And that keeps repeating over and over and over until you have your last period, where then you satisfy the demand of period T, capital T, with the production of period capital T plus the stock you brought from the previous period. So that is the process we are wanting to represent with our optimization model, and try to find what is the optimal plan in terms of how much to produce at each period and how much to send as an inventory from the period to the next. So in order to model that, we have to define some elements. So the main entity in our problem is the time period. So our planning horizon defined by capital T periods. P is the amount I'm going to produce at each period T. ST is going to be the amount stored in period T, meaning that this is the amount that is available to be used in period T plus 1. So I store today to use tomorrow. And I also have on that a production cost that depends on my time T, and a holding cost that doesn't depend on T, is the same, the cost to store. And I could say that I also have here my demand T. Notice that demand DT and PT, they are actually a time series, right? It's a time series for the price of my material, my raw material, and the time series for my demand. which I could have obtained using an appropriate time series method. Well, once that all is in, basically what I'm trying to do is I my decisions are here. So this is my step one, right? My decisions. Um, and basically what I'm trying to decide, well, what I'm trying to do is to minimize my costs associated with my production. So PT times little pt. So that's the amount of costs I have for production summed for all periods, plus my holding costs, which is the amount I held at each period times the holding costs. These two are within the summation, so you might want to use brackets to make sure that that is clear, but that's obviously what we're trying to mean. And the last thing to take into account is what are my constraints here, and I basically have only one constraint, which is the constraint that is doing the material balance of that node. So if I'm at node T, I have my demand leaving my node, my inventory coming from T minus 1, and my production at period T. And what gets sent to the next period as inventory from period T. So basically what we want to say is that these flows have to be the same. These flows, the input flows, they have to match the output flows. So it means that the amount I produce plus what I had from previous period as inventory has to be the same as what I used to satisfy the demand in that period plus what I send to the future as inventory. And that holds for all T, or that's better said, T is in the set 2 to capital T, because you can't have this constraint. Well, we can actually do a better job. We can just say that the T holds for everyone, but what happens is for T equals 1, this constraint becomes P1 equals D1 plus S1, because you don't have S0 defined. Okay? So you just have to be careful with whenever you have different indices in the same constraint, you kind of have to make sure you treat it in some way. And that's one way of doing so. You specify that there, either it doesn't exist this, or perhaps you can have a constraint with T equals 1. You could have like a parameter representing initial inventories. We'll play a little bit with these different ideas as well as we go in the course. We'll see these problems all the time as well. So here it is, our problem. Oh yeah, and of course these have to be greater than or equal to 0. Oh, excuse me, I just noticed that this is actually ST. And yeah, and that's about it. So that's the balance constraint, and this is the objective function that we try to minimize. Just as a remark, it might make sense to have inventory in some other contexts as well. So for example, when you have production capacity constraints, so it might be so that you're foreseeing a really large demand that you won't be able to satisfy immediately. So you might want to start production beforehand. Christmas sales is a big example of that. You start making Christmas products like decorations and all that much earlier, and you accumulate inventory until the end of the year. Another thing that can lead to inventory is uncertain demand. When it's not satisfying the demand is really expensive, you might want to play safe and have more inventory than average levels of demand, because it might be so that you actually have more demand than the average. And you also have to be really careful with boundary conditions with these models. It's basically because your model is going to see that the world end at periods capital T, the last time period. There is no reason for the model to have inventory to send to the next period. So what you're going to see is that these models tend to finish their plans with zero inventory, which might not make sense because the companies are not stopping to exist. So you kind of have to deal with these boundary conditions to make sure that, for example, you artificially augment your planning horizon to discard boundary conditions. So you're interested in the sort of the steady state of the process. This is not a unique thing feature for optimization. It happens with many models in many different applications, but it's just something for you to pay attention to. All right. Good. We'll stop here for now, and then the next part of this class is going to be about the geometry of linear programs. So see you in the next video.